it's only for recording, I guess.
Maybe down here.
Well, it's... I... First, hello, and thanks to the organizers for inviting me. I'll present the OpenBSD audio and MIDI framework for desktop application and for music. Actually, it's only a part of the audio subsystem. Well, first I will try to define the problem we want to solve after a short introduction about mostly vocabulary, definitions of audio, MIDI, and so. I'll try to define the purpose of the audio and MIDI subsystem, which is part of the operating system. Then we'll try to find what's the problem the audio subsystem is supposed to solve, and most importantly, what it shouldn't do. In the second part, we'll discuss design choices. Mainly the problem is, given we have the problem, how to solve it, how to pick the right approach, and to avoid the wrong ones. It's a long path, so I'll talk only about two aspects. The first one is whether the audio subsystem should be implemented inside the kernel or in Userspace. And then we'll discuss quickly which formats and algorithms we want to support, and which one we'll consider as out of the scope of the audio support of the operating system. The third part will present the solution of the problem we defined. Basically, we will see that the framework is built around an audio server, and I'll spend some time talking about synchronization and MIDI control, which are very important aspects of audio. And finally, I will try to show a few examples of how this stuff can be used in real life. And if it works, I'll try to present a short demo. So, first, general discussion. First, what is audio and which aspects we are interested in? Well, audio is a sequence of samples that are played at a fixed rate. The rate is fixed by the hardware, and samples are played or recorded by the hardware. An audio stream may contain multiple channels. That means that the sample number n of one channel is played simultaneously with the sample number n of all other channels. And that holds also for full duplex.
Or did you use
this one?
Yes. Okay.
Or so just okay.
Linux wireless.
Well, and that property holds also for full duplex streams. Full duplex streams are streams that have playback channels and recording channels. The channel number, the sample number n, which we play, is played exactly when the sample number n is recorded, and that will be our definition of an audio stream. This has two consequences. The first is that the audio hardware is a clock source. Since each sample, since samples are played at fixed rate, each sample is a kind of clock tick. Actually, we use blocks of samples. There are a set of fixed number of samples. The other important point is that samples can be streamed. Since they are played at fixed rate, buffers are consumed at fixed rate, so the time it takes to consume a buffer is deterministic. Well, that's a few important points that we'll use later. Now, what's MIDI? We'll talk a lot about MIDI. It's a simple serial link, which is slow. It transmits MIDI messages, which are events to control audio. This can be a start signal, a stop signal, a message to adjust the volume or whatever. Typically, messages are sent by the user or user equipment to control other equipment. It's a standardized protocol and is used by most professional audio equipment. Since it's old, it's very simple, and it's a real-time protocol, which means there are no timestamps involved. I mean, events are processed immediately as soon as they are received. All this means that MIDI cannot be a clock source like audio, but it can carry clock ticks. The other point is that it can be used to control audio. So in some sense, this is complementary to audio. So now what does the audio subsystem of operating system? It's simple. There, on one hand, we have the audio hardware. On the other side, audio programs, and there is a gap to fill. Mainly, audio programs and hardware may not support the same parameters, so the audio subsystem must do the necessary conversions. Multiple programs could want to share a single audio interface, so again the audio subsystem has to manage that. And finally, we often forget that audio applications have to work together, and they should be synchronized in order to perform a complex task. So this leads us to the goal of this project. Basically the problem we want to solve. Well, first, conversion and resampling is something that's necessary, since we want any program to work on any hardware. The other point is that we'd like application to share the same hardware. The most obvious way of doing this is to split a device, an audio device, to multiple sub-devices. For instance, if I have a 4-channel card, I would like to split it in two sub-devices. For instance, I would like to allocate channel 0 and 1 for telephony, and channels 2 and 3 for desktop music. So this way, I could run one telephony application and a music player simultaneously. This is the same problem as mixing two streams into a single one and sending the result to the hardware. So mixing and splitting in sub-device is the same thing. Only the way we process samples changes. Next point, the Unix philosophy consists in using small tools to perform complex tasks. Basically, for audio, this means that programs must be synchronized and they must be able to communicate. And that's part of the purpose of the audio and MIDI subsystem. And this aspect is somewhat novel in the Unix world, since traditionally we tend to use big monolithic programs, this complex, to perform complex tasks. And one of the purposes of this project is to allow small tools to be used together. The other aspect, the other constraint the audio subsystem of the audio subsystem is to do error recovery. That means that effects of transient error must stay transient. For instance, an audio and video player should not go out of sync if there is a temporary load burst. So we accept temporary degradation of quality if the system is not able to give enough CPU cycles to the audio application. But once the error condition is gone, there should be no degradation anymore. The other point, which is obvious, is that we don't want one program to break other programs by misbehaving. So there must be isolation between programs. And the last constraint, which is not specific to audio, is the correctness. We want the code and the architecture and APIs and all this stuff to be correct. And since, at least in my experience, it's hard to write correct code, which is complicated code at the same time, one of the main goals of the project will be to stay simple. Because, I mean, architecture must be simple, APIs we design must be simple, and tools should be simple if possible. And now we'll switch to the design consideration part. Now that the problem we want to solve is defined, we'll try to see which choice, how choice will be influenced by these constraints. So first, a small remark about performance and responsiveness. Performance is related to the CPU time consumed. And responsiveness is the time it takes to process an event. So for audio, performance is not a problem. We don't care about performance because audio consists mainly in moving blocks from one address space to another address space. There is no CPU usage for something useful. So, first approximation, the CPU usage of perfect audio subsystem is 0. However, delays are very important because they cause the sound to stutter. So responsiveness is of first importance for this project. Next, the audio subsystem could be implemented in Userspace or in kernel. And a question I often have to ask to reply to is, does it introduce extra latency? So the audio latency is the time between which a program produces samples and the user hears these samples. Well, since samples are buffered and that buffers are consumed at fixed rate, which is a sample rate defined by the hardware, the latency is proportional to the buffer usage. So the more we have buffers, the more we have latency. So it's not, it doesn't matter whether these buffers are stored inside the kernel or inside the user process. What matters is the buffer size and not where they are stored. So a kernel implementation wouldn't introduce extra latency as long as we control buffer size. But we should do it also for Userspace implementation. The next point is about stability. Is kernel implementation or Userspace implementation the most stable at fixed code quality? Stability is about whether the sound stutters or not. The sound stutters where there are loud bursts on the machine. So the program producing samples is not doesn't get enough CPU cycles to produce samples, and so the hardware doesn't get samples to play and plays silence or junk. During a load burst, Userspace components of the audio subsystem and the application itself may underrun. Kernel components cannot underrun because they are running at interrupt context, so they preempt any user process. So basically this means that during a load burst, the application, which is always running in Userspace, will underrun for sure. So in some sense we are toast. The underrun will occur anyways, no matter whether parts of the audio subsystem are implemented in the kernel or in Userspace. If there is one component that underruns, the sound will stutter. So a kernel implementation doesn't bring additional stability. So how to get stable audio? But the recipe is very simple. First, write programs that don't block, and then give them enough CPU to do their task. So the conclusion is that a kernel implementation would only complicate things. So the project will be implemented in Userspace. It's simple that way. I will skip. I will shorten the discussion about format supported, resampling algorithms, and so on. The discussion can be found in the paper, which is in the proceedings. The point is that there are plenty of audio formats and plenty of algorithms, and we have to make a choice. And so the choice for this project is to support only integer samples, or fixed point samples. The other one are either trivial to deal with or are not needed. So now we switch to the solution itself. I'll try to describe what the code does in some sense, and how it is implemented, and how it solves the problem I try to describe, given all constraints I enumerated. So first, a quick overview of the whole subsystem. It's built around an audio server that does conversions, resampling, mixing, and channel mapping, which is usual for most audio servers. It can split a device into sub-devices, and the property of the stream and constraints we apply to streams are stored in the sub-devices. So this is also a way to configure the audio subsystem by defining sub-devices. It has a per application volume that can be controlled through MIDI. It exposes a clock source for non-audio application, mainly useful for MIDI application. And it can control synchronization between applications. The last 2 points go in favor to the Unix philosophy, where we want to help small tools to cooperate. Then we have a MIDI server. It's not really a server, it's a simple software throughbox. A MIDI throughbox is a kind of hub for MIDI data. It's very common for connecting synthesizer with keyboards and any MIDI equipment. So we do this in software, and it's done in a way that doesn't make any difference between software and hardware. In other words, an application connecting to a MIDI port can connect either to real hardware or to a software through box. And finally, the most important point is that we define a library-based programming interface to access audio and MIDI resources in a uniform way. This means that the sub-devices exposed by the audio server are identical to real audio hardware. So the application doesn't have to care about whether it is using an audio server sub-device or real hardware. The API is very simple, hopefully. It mimics kernel APIs, which are based on the read and write system call. And all synchronization and error recovery is done inside the library and the audio server. So the application using this framework don't have to care about error recovery. Most applications that we run that are in ports actually don't care about synchronization and recovery. So this is a way to force application to be synchronized and to recover nicely from errors. The audio server is built on by elementary data processing units. Processing units have any number of inputs and outputs, and we have processing units to convert from one format to another, to resample. These units have typically one input and one output. There is a processing unit to mix multiple streams into a single stream, to extract channels. So they take one input and they split it into multiple outputs. And there are terminal processing units which are used for input and output, basically socket I/O and file I/O. They have either one input, either one output. These processing units are interconnected by FIFOs that carry audio data, and the whole things run inside an event-driven framework that is not blocking. It's event-driven, so it doesn't require threads. Anyways, using threads in such project is pointless, since the project is not CPU-bound but I/O-bound. So the audio servers is a particular configuration. It's a network of these units. Server behavior is determined by the choice of these units and the way we connect them. So I give an example. This is the network corresponding to a running audio server. Bullets correspond to processing units and lines to FIFOs. So we have, for instance, a socket which is using full duplex. It has an input and an output. The input is the playback direction, the output the recording direction. So the application sends audio data to this unit, then the data is decoded, resampled, and mixed with other inputs. The resulting stream is sent to the hardware device, and simultaneously the hardware device records samples, copies, extracts channels, and sends them on the sockets. And possibly, if necessary, can resample and encode into another format. Is it clear? Any questions about? Okay. The point is that if we remove the device and we just connect the output of the mixer to the input of the demultiplexer, this framework can be used as a general purpose conversion tool. For instance, we can build the following network. We can take one file, send its contents to a decoder, to a resampler, then mix it with another file, and then split the contents in two files of different format. So this is a configuration that can be used to convert one file format to another, or to split left channel from right channel, from a stereo file, and so on. So the next interesting point is the latency. There is a lot of buffering in this framework. So how the latency is controlled. Latency is important, especially for music applications. All we want is that it should be deterministic. Then the user, depending on his configuration, can select low latency or not. But the point is that we want it to be deterministic. So the latency is, as you have seen, the amount of buffered samples divided by the rate. But the rate is just a constant. And the number of buffered samples are the samples written on the sub-device minus the sample actually played. So this is what we consumed, and this is what we produced. And this gives what is left inside the buffers. So by controlling the number of samples buffered, we control the latency. And controlling the number of samples buffered is easy. We just have to control the number of samples we write. There is a theoretical minimum, however. A single application must use at least 2 blocks of audio buffers. 1 block for the device and 1 block for the application. That means that while the application is producing samples in 1 block, the device is playing the other block, and then it switches and so on. A server with independent application requires 1 extra block. That's why, for instance, if there are 2 applications and one of them fails to fill its block, it shouldn't break the other application. So there must be a kind of safe block to handle underruns. That's why the theoretical minimum for audio subsystem that can share the device is of 3 blocks. And this implementation supports this theoretical minimum. So the next point is how do we control application volume? Since we have a mixer, and mixer involves multiplying, scaling samples, basically this means reducing the volume of applications. We choose to control the volume through MIDI because it's simple, first of all. It's standard, which means that we can use existing applications or existing hardware. However, there are some limitations that we are working on. First, MIDI is basically just messages that go through a wire, and there is no standard way to expose application names, and actually such hardware cannot display. You see, there are only faders. There is no display on it. So we have to find a way to expose application names, to make the relation between application names and MIDI control. MIDI control is the fader. And the other limitation is that we don't have a MIDI control utility in OpenBSD yet. So for now the user must either use bulky hardware, like this one, or any applications that is found in ports. The next point is about synchronization. We want application to cooperate. This means that the minimum requirement is that multiple applications should be able to start simultaneously. We do it through MIDI also. There is a MIDI start message. And so it's very simple. When we receive a MIDI start message, we put the server in a kind of preparing state during which application prepare and fill their buffers. Once all applications are ready, the server starts playing all buffers simultaneously. The last point about MIDI is that there is an easy way to expose MIDI clock, the audio application clock through MIDI. This allows audio applications to cooperate with MIDI applications. I will show an example later. So this goes in the direction of the Unix philosophy, and as far as I know, this is the OpenBSD is the only open source, or I would even say only operating system to support this at operating system level. There are embedded operating systems that I guess have such a mechanism, but it's quite new on Unix. So I'll give a few examples of how it works. First, a complicated setup of that's typically what happens in big monolithic applications. So here, this is split on OpenBSD. This is split. This can be split in multiple small programs that interact with the server and with the hardware. So this part is the hardware. We have the audio interface, a MIDI keyboard, a MIDI synthesizer. The audio server plays and records a single audio stream on the hardware. This audio stream is the result of what applications send to it. So this is the bold lines are audio data. The server is can be controlled by a sequencer, MIDI sequencer, which can be also hardware sequencer, but let's suppose it's in software. And the sequencer can send feedback to all the applications through the MIDI through box. I'll try to show it as a concrete example. The integration in, but before that I will quickly present the integration in OpenBSD. Well, there is a single binary which acts as the audio server and can also be used as a general purpose player and recorder and conversion utility. So to start the server, you only have to type AuCat L. There is no configuration. Everything is given to the command line. For instance, to start the audio server and to create two sub-devices, you can specify that you want channel 0 and 1 to be the speaker sub-device, and channel 2 and 3 to be the headphone subdevice. And then application can use this identifier and this identifier as for audio output. Well, it can be used just to play a file, and all this required changing the name we name devices. So we used a similar approach as X. I needed device type, column, and a number, a unique number, dot, an option. So we will see that in a short demo. So first, first I will play two files simultaneously, just to show that that it works. So the setup we have is a running audio server connected to the hardware, and two players. So before we begin, all the demo will be built around three files, three wave files that are that's music at the same tempo, so we can mix them together. There is where is Brian? Brian is in the kitchen, and a voice mix. So let's play the first one. Yeah. I have to switch to turn off the video to get audio. So it works. It plays. I will open another one. So now both are playing, but it's not fun. You can't select one. So now I will connect. That's the current configuration, and we will switch to this one. So we add this part. Basically, we connect a MIDI controller to the audio server, and that is the MIDI controller. It's just like a keyboard. Just wait. It's for the musician what is a keyboard or a mouse for us. Just a bunch of faders that we can use for whatever we want. So I just will plug it. To plug it, have to say stop. I will use a through box. So this command connects AUCAT 0 and AirMIDI 1. AirMIDI 1 is this device, and AUCAT 0 is the MIDI backend of the server. So now they are connected, and I can start playback again. So see this stuff. Can you hear now? So when I move faders, it just works. Okay. So we can do this with voice also. That's actually I wanted this one. So we have voice and music, but it's not. They are not together. We want them to start simultaneously in order to sound better. I'm still not used to Japanese keyboard. So actually, you didn't see what I typed, right?
No.
Not a problem. So now we'll keep this link, and we'll send start and stop signals to the audio server, and we will connect these two players to another sub-device of the audio server that has synchronization enabled. This is the name of the sub-device. Okay, I type enter and nothing happens because the application is blocked. Okay, I start this one. There is no sound, it's okay. And now if I type the start button, I first will raise the sound. They are together this time. You can get only voice or only the accompaniment. Okay. So the next step, the last one would be to control this through an application instead of this the bulky MIDI hardware. So we will use a MIDI sequencer. So the MIDI sequencer will get clock ticks from the audio server and send start-stop messages to the audio server. And it will send start-stop and relocate messages to a through box that will forward it to audio application. That means that we'll be able to change the starting position of audio streams. So we put the players in slave mode. And we say they are controlled by MIDI through 0 device, which is a through box. Okay. So now we did just this part. We connected the through box to the audio players. Now we'll do this one, which consists in starting the sequencer and registering MIDI devices. That's the sequencer, simple MIDI sequencer, and that's it has a shell-like interface, and this is its syntax. I did a mistake, sorry. So now, if I start, if I send a start signal from the sequencer, everything will start. So I switch. Okay. So I push the play button of the sequencer. Forgot something. Sorry?
The volume is off on your mixer?
Indeed, yeah. Thanks. So I can stop it and go to a given position. And start it at, this is another position. And so to finish, we can do something more useful. Since we have a sequencer here connected, the sequencer can record MIDI events of the controller. That means that we can record the mix, the automation of the mix. So I will add a third file to play. Okay. Now we have, you see, yeah, we have 3 files, and I will create a track to store MIDI events sent by the controller. And we'll start recording. So I switch to audio. So there are 3 tracks. So I can keep just the music, voice only, music, and so on. So I stopped the recording. And no, that's not necessary. Okay. And now I can replay the same mix, which means I will start audio tracks all together, and the sequencer will send MIDI events to control the volume to the audio server and to this machine. So I'll put it this way. So I start playback. So this is what I did. And so well, so I skip the future work because we are late, and to shorten the conclusion, basically this is a framework for which is part of the audio subsystem of OpenBSD. It's very simple, has a single binary non-configuration. It's supposed to be stable by design, mainly because it's simple. It addresses most problems of desktop applications, converting, resampling, mixing, and so on, and try to address problems of music application in the Unix way, which means that simple applications will be used, should be used to perform complex tasks, and we have seen, hopefully, that with 2 simple tools, a command line sequencer and a command line player, we could record mixes and do stuff which is traditionally done by big monolithic applications. So that's all. Any quick questions?
So is it possible with these tools to do redirection over the network and whatnot? Like use like netcat to link like two processes on different machines and spread your stuff out?
Well, yes and no. Yes, because it uses Unix sockets for communications. So if you just replace Unix socket but TCP socket, it should work.
Sure, or just like netcat, right?
Netcat. No, you won't get with Netcat. You won't get all the synchronization mechanisms because they require a full duplex connection, and Netcat, as far as I know.
No, Netcat can do bidirectional.
Yeah.
And so can SSH. But you
Yeah.
have buffering effects.
Yeah, but that's not a problem. Buffer size are there is no way to say to this binary to expose the socket. I mean to redirect the socket on STD in or STD out. You can put whatever data you want, but on STD in, STD out, but it won't be the protocol itself. But that's should be trivial to code. You only have to add an option to expose. But I mean it won't bring you the same quality as a local program, and furthermore, the proper way of doing this is to change the socket type to deal with all the authentication, security, and such problems properly. But
assuming I don't care about that.
I've seen a thread on this of a guy using SSH and this tool for telephony. Poor man's voice over IP. Secure.
It's cool.
No other questions? Anyway, I will be around, so you can ask other questions private. Okay. Thanks.